Hello and welcome to my paper about ancient technologies as sustainable solutions to current ecological challenges. This video is presented at the 12th Experimental Archaeology Conference 2021. The demand for innovative solutions to pressing ecological problems is on a constant rise. Ancient technologies provide extensive yet underutilized opportunities to help solve such problems. In the next 15 minutes, I will illustrate some of these opportunities based on two technologies: ancient clay pot irrigation and ancient earthquake-resistant construction. The first technology is simple, comparably cheap. It is easy to get involved in experimental research as well as in application, and the impact can be observed in short term. The second technology is quite the opposite. It is complex. For experimental studies, you need an interdisciplinary team and money, and extensive planning and authorizations are required for the application. Let's take a look at clay pot irrigation. Clay pot irrigation is an ancient subsurface irrigation system based on locally manufactured clay pots buried in the ground. Seeds or seedlings are planted close to the pots, which distribute water directly to the plant roots, avoiding water loss and saving up to 70% of irrigation water. Different planting patterns are possible depending on the characteristics of the plants grown. The earliest preserved attestation of clay pot irrigation is a description of the cultivation of melons in the ancient Chinese agricultural book Fangsheng Qishu from the 1st century BCE. For the successful planning and application of clay pot irrigation, it is important to know the key properties of the pots, the soil, the plants, the environment, and the irrigation water. The most relevant pot properties include height, shape, volume, maximum outside diameter, material composition, firing temperature, both of them together determine porosity, wall thickness, surface area, hydraulic conductivity, and base diameter. Relevant soil properties include its hydraulic conductivity and salinity. Among the key properties of the plants are their root properties and water demand. Concerning the environment, local weather conditions, especially wind, and other factors like plants nearby are important. The vast majority of scientific studies is experimental, either lab or field studies or a combination of both. Currently, there are only two concise overview studies available in English. The most extensive publication of combined experimental and field studies is a German PhD by Thomas Stein. The majority of the experimental studies is concerned with analyses of the pot characteristics, especially seepage rates and wetting patterns. Other studies focus on the performance of the pots and the yield outcome when using saline or wastewater for irrigation. While lab studies are usually conducted with 1 to 6 pots, field studies can include a 2-digit number. Basically, all studies conclude that clay pot irrigation is an efficient technology in local small-scale applications in dry areas. Yet conclusions differ concerning the potential for large-scale applications, especially in terms of labor. What is lacking are replicable experimental study designs and more research that look at combinations of pot, soil, and plant properties to gain a better knowledge of how they interact most efficiently in a given setting. With enough data at hand, the aim would be to provide the scientific fundament for step-by-step guidance on how to efficiently set up a field in a given environment, including pot characteristics, planting pattern, watering schedule, and maintenance intervals. Clay pot irrigation has been applied in multiple development projects and became increasingly popular in community gardens around the world. The following brief examples were chosen to illustrate different contexts in which CPI has served as a sustainable solution to current ecological challenges. The Millennium Village project was conducted from 2005 to 2015 by the Earth Institute at Columbia University, the United Nations Development Programme, and Millennium Promise. It included a large-scale application of clay pot irrigation in the Hafsun district in Ethiopia. Almost 15,000 pitchers were distributed to grow sweet orange, mango, avocado, and apple. More than 1,400 households benefited from the technology. To quote Zenebe Woldu, "The system was generally found to be as much as tenfold efficient, saving 70 to 90% of water compared to the conventional surface irrigation method, in that there was almost no evaporation loss and infiltration loss was also negligible." In Bauchi State, Nigeria, clay pot irrigation was applied in agroforestry to combat deforestation and rural poverty. The project was conducted between 2010 and 2012 by the Environment and Development Foundation with funding by the GEF Small Grants Program. Quoting from the GEF SGP Nigeria newsletter, "This simple and affordable technique has enabled the people of Udubu, Katagum, Zaki local government areas in Bauchi State to reforest a whole Muslim praying ground, created several orchids and vegetable farms, and created jobs for women who make the pots." A project focusing on backyard gardening with clay pot irrigation in the Chotyari wetlands, Pakistan, was conducted in 2012 as part of the World Wildlife Fund Pakistan Indus for All program. To quote Saeed ul Islam and Naveed Ali Zumru, "With a compiled crop harvest data from 3 villages, a total amount of 60,000 Pakistani rupee net profit is recorded that highly advocates the introduction of pitcher irrigation system in arid and semi-arid regions at large scale in such a scenario of severe water scarcity and desertification issues that our country is experiencing." I am not aware of any studies analyzing and evaluating the long-term performance of pitcher irrigation in context of development projects, nor the experience of the people involved in a project or the problems that occurred and the applied solutions. A fundamental problem for research is the lack of collected and accessible data, regardless of whether a project was conducted by government agencies or non-profit organizations. This data gap currently prevents project-based research and comparative studies on a broader scale that will provide insights into how to improve future projects. Clay pot irrigation is an auto-regulative irrigation method especially useful in sustainable small farming, horticulture, vegetable gardening, and afforestation in arid and semi-arid regions. The technology addresses different sustainability development goals, among them no poverty, no hunger, and clean water and sanitation. Let's move on to earthquake-resistant construction methods. Ancient cultures in earthquake-prone areas around the globe developed individual, often local solutions to improve the seismic resilience of their structures. Earthquake-resistant construction is of course a large area of research involving numerous disciplines. Interdisciplinary research in ancient and traditional building materials and building technologies has become a larger field during the recent decades. In the early 90s, archaeoseismology began to evolve, the study of past earthquakes based on the analysis of archaeological evidence. Research focusing on the sustainable protection of ancient structures and buildings in earthquake-prone areas is increasing, but only a small number of studies is concerned with the seismic properties of ancient structures and their experimental exploration, and even fewer studies look at the potential of these ancient technologies in modern contexts. Currently, there are several research gaps that need to be addressed. We need more interdisciplinary research on the performance of ancient earthquake-resistant technologies and their potential applications in modern contexts, including the development of hybrid solutions. We also need systematic combinations and evaluations of existing studies and their results, as well as overviews of the available methodologies and technologies for experimental research. Let's take a closer look at 2 applications of ancient earthquake-resistant technologies in modern context, the Tokyo Skytree and Daji Dewari. The Tokyo Skytree is the tallest tower and the second tallest structure in the world, with a height of 634 meters. The ancient technology applied in its construction is the Shinbashira, a central pillar used in ancient pagodas. The 122-foot-tall pagoda at the Horyuji Temple in Japan was built in the late 7th century AD and is one of the oldest wooden buildings in the world. It was added to the UNESCO World Heritage List in 1993. In Japan, no pagodas have ever suffered serious damage from earthquakes. The tower is an excellent example of a hybrid solution, the combination of ancient and modern knowledge to get the best result. On March 11, Tokyo Skytree, still under construction, was shaken by the Great East Japan earthquake. The tower withstood the quake without any damage. To quote information provided by the government of Japan, one of the reasons why Tokyo Skytree withstood the enormous quake was the vibration suppression system used for the first time ever, known as Shinbashira Seishin, Center Column Vibration Control. The core section of the main structure of Tokyo Skytree is a void measuring 10 meters in diameter, which extends up to a height of about 475 meters. a cylindrical column made of reinforced concrete measuring 8 meters in diameter and 375 meters in height, called the Shinbashira, has been installed through the void as if piercing Tokyo Skytree. Even though the Shinbashira is structurally separated from the main tower structure, the two are joined by steel beams up to a height of 125 meters, and via devices called dampers that suppress vibrations by stretching and contracting in the sections above. The Shinbashira is heavier than the main tower structure, which is made of steel and barely vibrates. As such, the Shinbashira and the main tower structure behave differently when shaken by an earthquake or storm. If the two move in opposite directions, the vibration is cancelled. It is said that the Shinbashirization system reduces seismic vibration by up to about 50%. Following the October 2005 earthquake in Kashmir, over 100,000 homes were reconstructed by using the indigenous construction of Daji Devari. Houses of this type performed much better during the quake than other building types, and Daji Devari was also selected for speed, cost, and availability of materials and skills. The performance of this construction was so well that the Earthquake Reconstruction and Rehabilitation Authority, the official body of the government of Pakistan responsible for reconstruction and rehabilitation in the earthquake-affected areas of Pakistan and Pakistan Admires Kashmir, encouraged the use of Daji Devari for construction of housing units. Daji Devari literally means interconnected or patchwork quilt wall. It is a traditional timber-braced frame with random rubble masonry infill construction, practiced mainly in Kashmir, but also found in mountainous northern parts of Pakistan and India. Daji buildings are mostly single-story structures with wooden pitched roofs. The earliest known half-timber building I'm currently aware of is the rebuilt Opus Cartesium house in Herculaneum, which was built before 79 AD. Opus Cartesium is described by Vitruve in his second book about architecture. During the Middle Ages, the half-timber structures were widespread in Europe, known as, for example, Fachwerk in Germany, Colombage in France, and half-timber in the United Kingdom. During the Ottoman Empire in the Middle East, the wooden frame structures diffused also in India, Kashmir, and Turkey. At the beginning of the 19th century, Daji Devari construction became one of the two main traditional construction systems in Kashmir. Ancient earthquake-resistant construction technologies have the potential to address the sustainability goal, affordable and safe housing for all. To quote archaeologists and engineers on the matter, Ravi Sinha, Svetlana Bretsev, and Gayatri Karel said in their presentation about indigenous earthquake-resistant technologies an overview. The use of indigenous earthquake-resistant construction technologies provides an excellent opportunity for large-scale construction of earthquake-resistant housing in development countries at relatively low cost. However, there is a need to greatly expand the research and development activities in this field to further improve these technologies and make them acceptable as modern construction techniques. Klaus G. Hinson writes in his abstract about advances in archaeoseismology. Quantitative models also provide perspectives for discussions about historical building techniques, such as the existence of ancient earthquake-resistant construction. The results of such investigations can improve efforts to preserve the cultural heritage of a region and can be utilized to avoid future construction mistakes. And A. Bayraktar, H. Kaipur, and A. Naderzadeh state in their presentation about the application of ancient earthquake-resistant method in modern construction technology. This paper explains some details of the analytical procedure to prove why layered cut stones have prevented seismic waves to enter the structures in ancient structures. More investigation on the analytical aspect of this method can offer the details on how this method can be applied in modern earthquake-resistant construction technology. My objectives for this presentation were to raise awareness for applications of ancient technologies in modern contexts and to illustrate their potential as solutions in context of the Sustainable Development Goals. If you are an archaeologist and you want to get engaged in solving current ecological problems, ancient technologies in modern contexts is a cutting-edge emerging field of research that offers you the opportunity to combine both. Thank you for your interest in this presentation.